In this lecture, I am going to explain the determination of location of neutral axis of a composite column subjected to combined axial compression and bending. So, this is the interaction equation of a column subjected to axial compression and bending. So, this is said to be Mn interaction curve. So, as I have explained in the earlier lecture, where the point A is under pure compression case, point B is pure bending case, and C is a point where the column is subjected to compression as well as bending. In the design process, this point D is not to be taken since it shows a capacity larger than the plastic resistance of the column cross section. So the point at C is nothing but it has the capacity of the complete plastic capacity of the cross section and also subject to the axial compression. The amount of axial compression at the point C is nothing but twice the compression which is determined at a point C. In the earlier lecture, I have explained what is the capacity of this point D. So the point C is nothing but twice the capacity of the point D. Therefore, the capacity, the stress state at the point C is nothing but axial compression of NCRD, which is equal to twice the resistance in the point D. And the plastic resistance at C is equal to the plastic resistance of the column cross section. So where it is computed by this expression. This is the stress block we have seen in the previous lecture. That is, to get the stress block of point C, it is derived from the stress block from B. So from this expression, it is well known that the stress at C is nothing but the plastic resistance of the whole column cross section and a compression NCRD, where NCRD is nothing but twice the NDRD. See here, to calculate the plastic resistance of a column cross section, you have to use this expression. So in this expression says that you have to calculate the plastic section modulus of concrete portion of the whole cross section, concrete portion present in the whole cross section, minus the same concrete which is in the core region, that is this region. What it says that if this is the case, here there is a concrete, the concrete section modulus has to be calculated as a whole from the whole gross cross section, that is nothing but ZPC. ZPCN is nothing but the amount of concrete which is present within the distance. Say this distance is said to be 2HN, that is from the CG of the cross section, the neutral axis is available here. So this distance is said to be 2HN. So within this 2HN, you have a concrete. To calculate that concrete section modulus, and that is represented by ZPCN. Then you make a algebraic sum of the two, that is the whole concrete plastic section modulus minus the concrete section modulus within the core region, that is this region, 2HN region. Similarly, coming to structural steel, this is ZPA is nothing but for the structural steel, you calculate the section modulus of the whole rolled section. Then you subtract the portion of the steel which is available within this 2HN region. Then you get what is the section modulus of the of this case. Similarly, this is a rebar. So in the case of rebar, this is said to be for the whole section there are 8 bars are available. Calculate that 8 bar plastic section modulus, where PSN is nothing but the amount of bar present in 2H region, that is the 4 bars. You calculate the plastic section modulus of this 4 bars and you substitute here, you will get what is this expression. So if you substitute the respective values in this expression, you will get what is your plastic moment of resistance. So from which you have to know what is the location of this HN distance from the CG of the distance. So from the upper portion there is a HN, below the central axis you have an HN. So the total height of this region is said to be 2HN. So here we are going to see how to locate the distance of your neutral axis from the CG of the cross section. To locate that, you have to consider two axisymmetry axis, that is two inertia axis, about major inertia axis as well as minor inertia axis, because the column is subjected to bending about major axis. In that case, you have to locate the neutral axis with respect to major axis. So in this slide, I'm explaining how to locate the HN distance, that is 2HN distance, that I have shown it in this hatch pattern. How to locate this 2HN distance about the major bending axis, assuming that the column is bends about major axis. So here, to locate this HN distance, since the cross section is not made up of one material, since it's made up of more than one material, therefore HN is taken in three cases. One is the HN will be within the depth of the steel web section, or within the flange of this steel section, or beyond this flange of the section. So in this case, I have taken a case that is my 2HN region is within the web of the steel section. That is why I put this condition. So I have given some nomination here. So this is the breadth of the I section, this is the height of the I section, this is the breadth of the column, this is the height of the column, within which I'm going to locate what is the core region in which I want to calculate the section modulus, plastic section modulus, to calculate maximum plastic resistance of the column cross section. So here what I am doing is, from this I'm going to locate the location of neutral axis such a way that I say that this is the height of the column. So height of the column divided by 2 minus TF. That means I am mentioning my HN should be within this region. So if that is the region, I am going to calculate the NCLRD, that is AC into FCD, is obtained by equating the compression controlled by the material available in the 2H region. That is, ACFCD is nothing but NCLRD, which is equal to the compression controlled by the material available in 2H region. So the compression controlled by this 2H region is nothing but compression controlled by the concrete, reinforcing steel and structural steel. So to calculate this compression controlled by this material, so I'll calculate like this. So here what I am doing is I am taking the gross cross-sectional area of this 2H region, that is BC into 2HN into FCD. So I am calculating the gross cross-section, and what I am doing is I am going to add the contribution of the compression contribution of the structural steel by taking the corresponding area, that is this height will be 2HN and this thickness is TW. So this is area which is embedded within the concrete. Therefore, what I am doing is I am going to take the steel alone, eliminating the portion which is already taken in the gross cross section. So in this region, the stress in the structural steel is found to be 2Fy. Please refer my previous lecture about the stress. So in this 2H region, my stress in the structural steel will be 2 times FYD, that is design stress in structural steel, minus concrete stress. Why I am making this minus? Because in this core 2H region, the reinforcing steel is embedded within the concrete. It is not possible to get the concrete area directly. Therefore, I am taking gross area and deducting the concrete area in the respective calculation. So coming to the reinforcing steel, here I represent A-ST is nothing but the amount of reinforcing steel available in the 2H region. So which is equal to 2 times FCD. This is the compression controlled by the reinforcing steel. I'm minusing with the stress in concrete. That is this amount of concrete to be eliminated. From this expression, you can able to arrive the expression for HN for the case of when your HN is less than this region, that is within the web of the concrete. If you consider the second case, that is if the HN is within the flange, that is beyond the web and within the flange region. So in this case also, following the same principle, I am equating the NCLRD to the compression controlled by the core region. So here again I take the whole gross area of that core region. Core region means here I am mentioning 2HN region, and I am taking this is the area of the web web portion, and this is the area of the flange part, and I'm taking the area of the reinforcing steel as explained in the earlier expression. From this I'm calculating what is your HN. So it depends upon the location of the neutral axis, you have to calculate HN. In the third case, your HN is beyond your flange. So this is the case. That is, here it is beyond the height of the reinforcing steel. That is why I have given HN is greater than H by 2. In this case also, I have taken the gross area of the 2H region. Since the rolled section is completely within the 2H region, so therefore I'll take that region into the respective stress. In the respective stress, as I told that the stress in the structural steel is 2 times FYD. I'm deducting the concrete which is already accounted in the first term. Similarly, in the reinforcing steel, from this I'm calculating the expression for HN. So this will be useful to identify how much region going to be in the 2H region in the particular case. If I know the HN distance, I could able to know the region in which what are the materials are available. For example, if this is my 2H region, I should calculate what is the plastic section modulus of the component which is available within this region. So if I know this region, I can substitute. This is the component, nothing but the plastic section modulus of structural steel within the 2H region. This is the amount of concrete within the 2H region, that is plastic section modulus of concrete within the 2H region, and the reinforcing steel in the 2H region. Where the first term is nothing but this is nothing but taking the whole section without the core, taking the whole section BC by HC, where you have a rolled steel section, reinforcing steel and concrete. You calculate that section modulus independently and substitute in this expression to get plastic moment of resistance about major axis. So please follow this definition. Plastic section modulus is nothing but the static moment of area above and below the equal area axis. So this is about the minor axis. So this is your minor axis. In the minor axis case, your HN category again comes into 3, where you can take from the CG of the cross section in the minor axis direction. Your HN will be within the TW distance, then within the BF distance. So that I have explained here. This is first case, that is my core region, 2H region will be within the web depth. So this is very, very rare. In the minor axis case, you may have the second case or the third case. The second case is nothing but it is greater than the thickness, half of the thickness of the web, and it is less than this this B by 2. So this is the case. If this is the case, you take this region alone as your 2H, calculate your section modulus and substitute in your expression. That is for the cross section about minor axis. Here you take third case where the 2H region is going beyond the B region. So it is within the BC by 2, because always we represent HN from the CG. So it is greater than B by 2 and it is lesser than BC by 2. So this is the way you calculate the HN distance about minor axis. If I know the minor axis, then I can able to calculate the plastic resistance of the cross section about the minor axis. That is taking the whole section plastic section modulus of a structural steel about minor axis, and the 2H region structural steel plastic section modulus about minor axis, and so on. You can substitute it, you'll get what is the moment of resistance about the minor axis. Thank you.